I'm Josh Young, and this lecture is on the optics of new intraocular lenses. First, my disclosures. These are the companies that I either run or consult for. In days past, you would go to the coffee shop and the choices would be coffee or not coffee, perhaps cappuccino, later on maybe decaf coffee, but that was it. Now when you go to Starbucks or somewhere similar, there are a lot of different coffee options that demand some level of education of the consumer to figure out what it is that he or she desires. Well, the same thing's going on with intraocular lenses now. The choice used to be cataract surgery or no cataract surgery. Now there are multifocals. Well, now there are more than just multifocals. There are extended depth of focus lenses and even different sorts of extended depth of focus lenses. And how can we educate ourselves to make the right choices with our patients? An analogy that I think is helpful is that of sound. So because it's a little bit easier for us to conceptualize than what some of these terms mean in terms of light. So let's start out with sound. This is a quote from Elon Musk that I'm now going to play.
With artificial intelligence, we are summoning the demon.
So that was a clip with a lot of noise, and now let's hear this one.
With artificial intelligence, we are summoning the demon.
One of my favorite quotes of his. So let's, we understand that the first audio clip was very noisy and the second one was relatively noise-free. Let's kind of put terms on things. So the top image here, the upper left hand, is an image of the sound wave of the signal, just Elon Musk's voice. The one on the bottom left is the noise, and the two of them combined make that noisy clip that we heard at the start. Let's substitute now some optics terms for these same sorts of things. There's the object, there is noise in the optical system, and the result is an image with noise, just like that clip from Elon Musk. The signal here are the rays of light that are coming from the object, and the noise is what we're going to call the point spread function. And the combination of the object and this point spread function gives us our image in the same way that the combination of the pure unnoisy audio track and noise gives us our final product of that noisy audio track. And in the same way that the noisy audio track makes it more difficult for us to resolve what Elon Musk is saying, similarly, the noise that's introduced by the point spread function and the object together make it more difficult for us to resolve what the actual object is. Now, we're taught that optical systems look like this, that the rays of light come in parallel, they converge to a single focal point that is a point that is dimensionless, that it's literally just a point. But real optical systems aren't like this. First of all, even perfect optical systems that are out of focus or have some other shape or orientation to the lens can give us something that isn't just a point, but a point sort of smeared out. This is examples of different points. We're going to call them point spread functions because we're going to be modeling them mathematically. So let's call them point spread functions now. So these are different point spread functions for different orientations and shapes of the lens through which the parallel rays of light will pass. A piston simply means moving the optical system forward or back. Tilt is tilting the lens, and you see that the point spread function shifts to the right or left or up or down. And then astigmatism causes the point spread function to spread out in characteristic ways, in ways that we can identify as having come from this sort of an aberrant optical system. We have words for coma, but then, once we get into higher order aberrations, the point spread functions don't really have names that we use. We'll talk about a fourth order aberration, a fifth order aberration, that sort of thing. So when we think of light passing through a lens, we draw it out in rays, but what's actually going on is a sort of a wave of a cohort of photons coming in. So on the left, you see this cohort is coming in as sort of even ranks as these nice vertical columns and hitting the lens and being bent by the lens to converge. What we're showing here is wavefront. So we have this planar wavefront coming into the lens on the left and is being bent in a manner to converge, as is the case with a converging lens. So these are rays of light, a wavefront with plus vergence. And on the right-hand side, this greenish one is an illustration of rays of light with negative vergence. They are diverging. But real wavefronts don't look so pristine. So this is a simulation of a wavefront of light coming from a distant star. And, it makes it the X number of billions of miles here relatively undistorted, but then hits our atmosphere and is distorted by different densities in our atmosphere with different local indices of refraction that causes the wavefront to distort. How can we quantitate this wavefront so that we can do something like arise? We can derive the actual point spread function. So the classic way of doing this is by passing the wavefront through a series of apertures that are arranged in a grid. And the rays of light will pass through the aperture and then be focused on a screen. Focused because in our aperture we're going to put in little tiny lenslets that focus the ray of light. As long as the wavefront of the light coming in is planar, it will be equally spaced on the detector, on the screen, on which the little rays of light are focused. If the wavefront is distorted, as we saw in the case of the telescope, these little dots will be displaced. So planar wavefront, all of the little dots on the detector are in the same pattern, the same spacing as the lenslet grid. If the wavefront is distorted, then the little lenslet images will be shifted too. We call this a Hartman Shack aberometer, and this is an example of a lenslet capture in the real world, an ideal eye and an actual eye, and using math, we can calculate what the shape of the wavefront actually looked like. And from the shape of this wavefront, we can then calculate what the aberrations were in the optical system that generated this wavefront. And we do this by modeling the wavefront using a series of polynomials called Zernike polynomials. And we add different Zernike polynomials to replicate the shape that was captured by the Hartman Shack aberometer. You'll notice that the terms used here, piston, tilt, astigmatism, trefoil, these are the same terms that we saw with the point spread functions earlier, and we can translate these things into point spread functions. And just to show you my street cred, this is a rather sweaty Dr. Young at the Museum of Zernike Polynomials. Real point spread functions don't look exactly like that. Real point spread functions are a little bit of a mess. They don't follow any of the patterns exactly on that pretty point spread function chart that I showed you. They're irregular. Where is this point spread function? Where are these points? So these points are where the rays of light converge. And this is an image of green rays of light converging from a monofocal IOL. You see, they come down to a point-ish. It's not exactly a point. That is right where that little red circle is. We're going to zoom in on this point, but before we do that, we're going to rotate it vertically. So this is the same thing, but rotated vertically. And we can plot out things like the intensity of the light, the density of the photons in different parts of this 3D structure. And that is what these maps here are. So when we're saying point spread function, what we're talking about is where this 3D structure intersects a screen or the patient's retina. We're going to look now at one particular point spread function, and the only one that I know of, with an eponym. So what we've done here is we've mapped out the point spread function with intensity plotted along the z-axis so that the light is most intense right in the center and then wanes as it goes out. But you'll notice that it doesn't wane uniformly. It goes out, and then there are these little ripples that propagate out from the center. This point spread function we're going to see later on is an Airy disk that some of you may have encountered, particularly if you use a device like an IOL master. You can see that when it is in good focus, all of the little dots are in fact little Airy disks. We'll see more Airy disk pictures later. What creates these things? Well, we know that there is diffraction of light that occurs if an aperture is small. But even if an aperture is not particularly small, there is diffraction that occurs at the edge of the aperture. There are diffractions that occur at the edge of the pupil. FYI, this is why resolution with a really small pupil is, meaning one that's, let's say, 1 millimeter wide, is not as good as resolution in an eye with a pupil that's a little bit larger, maybe 2.5, 3 millimeters wide, because there is some limitation to the resolution as a result of the diffraction off the pupil edge. But, you know, that's a digression. So what does this aperture produce? What does it look like? So it looks like this. We'll have a very bright area in the center, followed by concentric alternating areas of darkness and brightness. Those are the little ripples on the side of the peak that I showed you in the previous slide. So this is an Airy disk, and those little ripples are the feet. And the word, our fancy scientific word for feet is of course pod, like tripod. And if we want to maximize the signal in the center and reduce the signal in these little feet, then we want to cut them off. We want to make a curve that is apodized, which is a term that you may have heard with some intraocular lenses, are apodized lenses to reduce the amount of light going into these little ripple-like fluctuations on the outside of what we want to be a central bright point of our point spread function. And this is just examples of a signal on the left with the little feet, what the signal looks like in the middle column and what the feet look like on the side. So we can see that apodization may be something that is beneficial, but again, only in the circumstances in which we have these idealized point spread functions. So we think of point spread functions maybe as looking like these Airy disks on the left, or even this beautiful trefoil point spread function here, but real point spread functions are a mess. They look something like this, and what we want to do, obviously, is to get the noise out of this system, or at least to create an optical system that minimizes noise. So I've shown you now 3 times this beautiful print of an Airy disk. What do real curves look like? They're asymmetric and messy, and this is an example of a real point spread function. So what does this point spread function mean for the patient? This is an example of different multifocal and monofocal intraocular lenses. I guess these are all multifocal. And the point spread function is viewed as a smearing of points for the patient, particularly at nighttime. So the point spread function is something that we want to address and something that we want to keep in mind. But how are we going to relate point spread function to a particular lens? Now we're going to get into some math that's heavy, but I'm going to keep it non-quantitative. So this, once more, is a point spread function on the left. And what we're going to generate on the right, our goal is to generate something that we're going to call a modulation transfer function, an MTF. The MTF is the fast Fourier transform, FFT, of the point spread function. What on earth does that mean? Well, if we were to take a section through the point spread function, a cross section through it, we may get something that looks like the drawing on the right. Now, obviously, the one on the right does not exactly correspond to the one on the left, but you get the idea with the central peak and then these little ripples going out. We can describe any curve as the sum of a number of sine waves. So here we are going to take a sine wave, this is the sine wave that we're going to generate, and you see we've got different radii of curvature for this circle, and as we add up sine waves, the added wave is the one with the profile in blue. We can get any arbitrary complex shape. How arbitrary? Well, this is my favorite example of a series of sine waves adding up to a very complex shape. Why do we bother doing this? We bother doing this because the MTF, the modulation transfer function, which, as I say, is the fast Fourier transform of the point spread function, tells us a lot about the performance of the lens. So I've been saying the MTF, modulation transfer function curves. What does that mean in real terms? Modulation can be thought of as contrast, sort of. So if we take on the upper left-hand corner there, this absolutely perfect pattern of black lines and white lines, if we were to plot out the intensity, it would be this square wave that we see directly underneath these bold lines. But when we pass this object through an optical system and we create an image, the image is necessarily imperfect. And the imperfections show as a sort of a rounding of this square wave. So we get something that looks more sinusoidal, and you can see that the image on the right, that the white bands are more spread out, more diffuse than they are with the object on the left. However, the areas of greatest brightness and the areas of greatest darkness are still as different from each other as they were in the original object. But if we begin to space the lines in our object more closely, if we pack in more lines per millimeter, line pairs per millimeter, LPP, line pairs per millimeter, LP, excuse me, then we can get enough crowding of the little peaks in the image that the difference between the brightest and the darkest areas of the curve are less. There's less of a difference than there was in the original object. And there's less than there was in the case of a banded pattern in which there are fewer lines per millimeter, in which the lines are spread out more. What does this mean in terms of an optical system? It means that contrast, which is going to be our stand-in for modulation here, that contrast decreases for any optical system as the line spacing goes up. So a perfect modulation transfer function curve would look like this, meaning that as the line pairs per millimeter goes up as we go to the right on the x-axis, the modulation or contrast goes down. Now, I've just gotten done showing you all of these perfect curves and telling you that the real world's not like this, and indeed it is not like this. So this is an example of a point spread function shown upper left there in figure A. Figure B is just a cross section through that. Figure E is the modulation transfer function, the Fourier transform of the above point spread function. And you see it does not slope down evenly. It drops down rapidly at the start and then just sort of bumps around as the line pairs per millimeter increase. These are just more examples of different sorts of point spread functions. And the modulation transfer functions, which are themselves 3D, we're not going to worry about that yet, although we are going to return to that concept. What does this look like in the real world? Figure A in the upper right-hand corner, you can see that the contrast decreases as we go to the right. B is the same as image A, but it's out of focus. It's defocused. And with A, there is this sort of linear drop-off in contrast as we go from the left to the right. Whereas in B, there's a precipitous drop-off in contrast at the start, and then it just sort of plateaus with terrible contrast from about halfway through the image on out to the right. The two modulation transfer function curves that describe A and B are shown in the lower right-hand image. The one that's marked aberration-free is like what we see in image A, where the contrast drops off gradually as we move from the broad spacing to the left to the fine spacing on the right. The curve that's drawn in that sort of purplish blue, the one that's marked OTF/MTF, that's optical transfer function, modulation transfer function. We're not going to worry about the terms. Let's stick with MTF. You can see that drops off precipitously at the start, and by the time that we're at a frequency of about 0.2, the contrast is essentially gone. And you can see that, again, by looking back at image B, seeing that the contrast really precipitously drops off, so that when we're about a third of the way into that image, everything is just a fairly uniform gray. And the difference, again, between A and B is defocus. As we change the focus in an optical system, the MTF, the modulation transfer function curve, is going to start looking less and less linear and more curved down, more of a drop towards the start. So the difference between 1 and 5 here is how much out of focus it is and how much loss of contrast there is for each degree of out of focusness. 1 being in focus, 5 being very much out of focus. So what are we seeing on this whole graph? We're seeing MTF, or sort of contrast, in the y-axis, spatial frequency in the x-axis, and the different colors are showing us the different degrees of focus. What does this look like in terms of lenses? So this is an example of different monofocal lenses with different diopters of defocus, and contrast MTF shown on the y-axis. So that when we're in perfect focus, contrast is high, and depending upon the lens model, contrast will drop off at whatever rate the lens was designed for, as we move to the right or to the left. One thing that I do want you to notice is that the area under these 3 curves is about the same. The difference is the distribution of that area, and we're going to revisit that idea later. Okay, we've seen here these sort of defocus curves with modulation transfer function. Let's work our way to MTF curves that are more similar to what we are going to encounter when we're evaluating different lenses. So this is just my graph of an example of a bunch of stacked modulation transfer functions. And you see the one in the darkest green has that nice linear decrease in contrast as we move from widely spaced lines on the left to very closely spaced lines on the right. And the curves that dip down more are ones that are out of focus more. I'm going to rotate this graph. So I just want you to once more observe what this is. This is lines per millimeter on the x-axis and modulation on the y-axis. And what I'm interested in is the defocus. What happens to this particular lens as we reduce focus? So I'm rotating this graph now so that defocus is now on the x-axis. Whoop. Let me go back one slide. There we go. That defocus is on the x-axis. And this is a funny looking lens, right? As we move from the left to the right, there are these undulations. It looks like one of those carnival slides people go down with the little different chutes. Okay. Let's take one particular target, a certain number of lines per millimeter, something arbitrary, something in the middle, and take a cross section through this curve. What do we get? So this is a cross section through this sort of MTF body here. And we have modulation, contrast on the left, and we have defocus in the x-axis, where good focus is all the way to the left. We'll call that plano. And more and more need for plus power as we go to the right, or more myopia as we go to the right. And you see that we have 3 peaks here. So we have an area where the modulation, where the contrast is very high, and then it dips down as we get a little bit out of focus, and then it goes back up as we're medium out of focus, and then it goes back down, and then back up as we are quite out of focus. So let's kind of put numbers on things. Maybe this first peak is at plano. Maybe the second peak is at maybe plus 125, and the third peak might be at plus 250. And this would be the modulation transfer function for a trifocal lens. But I want to specify, again, this modulation transfer function and all the ones that we're going to see going forward that are these lines with these little bumps, they are specific to a specific number of lines per millimeter, a specific object that has got lines that are spaced out at a certain frequency. What happens if we choose a different frequency? The relative heights of the peaks change. They change as we choose different spacings. So, for example, this is a modulation transfer function at a particular object, a particular target with a particular number of lines per millimeter. And we see that there are two peaks here, right? So right away that tells us this is a bifocal, multifocal intraocular lens. It's a bifocal lens. The first peak is at 0 at plano, and the second peak here is at +4. And again, that's +4 at the IOL plane. It's going to translate to something less than that at the spectacle plane, probably something more like a +3 or +2.75. I showed you an example at the start of monofocal lenses with different curves, and I told you that the area under each of the curves was about the same. We're going to revisit this idea of the area under the curve. That area under the curve represents all of the photons coming into this eye, and we're going to call this a photon budget. So let's say that we start out with a $100 photon budget, and we're going to dedicate some of that budget to one of the peaks and some of the budget to a different peak, knowing that our budget is limited. We can't make more money. But before we can split things up, we actually have to pay a tax. And the tax is some of the photons are lost to destructive interference at the diffractive element of the lens. And this varies. It can be 14%. It can be as low as about 9%. It really doesn't get much lower than that. So let's say that this particular lens that we're dealing with, we have a $14 loss just as a result of the diffractive element. That leaves us with $86. We get to spend this $86 on distance and at near. And I'm going to show you two lenses here. One of the lenses is the Restore 3.0 and the other is the Restore 2.5. Now, we know, you can guess, that the 2.5 has got less add than the 3.0 does, and that's true. But all that add tells you is where the peak is. It doesn't tell you how high it is. The height of the peak is given by the budget. In the case of the 3.0, 59% is spent on the distance peak and 25.5 on the near. Whereas the Restored 2.5, you can see, is predominantly a distance lens with only about 18% of its budget spent on reading. So think of what this would look like, right? We're going to have our main peak at plano, and we're going to have a peak at 2.5 for the Restore and at 3 for the Restore 3.0. But the 3.0's peak is going to be higher. So let's see what the actual curves look like. Now, I couldn't find a graph that had just these two lenses, so we're going to have to work with this one. The 2.5 curve is in green, and the 3.0 curve is in red. And you see that the peak for reading, that's the peak on towards the right, for the red is higher than the peak for green. But that has to come from somewhere. That budget has to come from somewhere, and it comes from the reduced contrast at plano. So the Restore 3.0 is going to have a lower modulation transfer, a lower contrast at distance than the 2.5 is, in addition to having a higher plus add. Now, we're looking at the different distributions of different lenses here. How do any of these compare to monofocal lenses? What if we were to spend all of our budget on achieving the maximal contrast at distance? How does that compare? Well, there's no comparison at all. The monofocal IOL has a much, much higher peak. This is why we implant monofocal IOLs in patients with maculopathies, because for those patients, our goal is to maximize contrast, and we can't sacrifice contrast to achieve these multifocal tricks. Okay. And indeed, there are many people who advocate not implanting multifocal lenses in patients with glaucoma for the same reason, that we want to maximize contrast for glaucoma patients. This is not a modulation transfer function curve because on the y-axis here is not contrast. On the y-axis is acuity, and acuity and contrast are a little bit different, and I'll illustrate that in slides going forward, but take it from me. When we're talking acuity and when we're talking contrast, we're sort of talking different things. This is a slide that shows the difference between a monofocal IOL and an EDOF lens, an extended depth of focus lens. We can see that the extended depth of focus has acuity that is still pretty good, even as we defocus things more and more, whereas the monofocal lens, the acuity drops off much more rapidly with defocus. This is an example on the left of a bifocal IOL, and on the right of an EDOF lens, an extended depth of focus lens. So what do their relative point spread functions look like? Well, it's not helpful to just look at a point, but to again view this more in 3D. So this is a monofocal lens that has got a distinct single focus, where the 3D point spread function here looks like an hourglass. Things wasp waist down to a single point. This is an example of, well, look at that. Two distinct foci, and this is a bifocal multifocal lens. This is a lens in which the point is more spread out. The hourglass is sort of stretched to create a longer area in which the point spread function is still relatively narrow. So this is an example of an extended depth of focus point spread function in EDOF lens. Here are examples of different bifocal and trifocal lenses. This does not have the MTF of the newest trifocal lens at the time of this recording, which is the Alcon Panoptix lens. But we see here the green is our old friend, the Restore 2.5, which is primarily distance, has that little second peak for reading. The 3.0 Restore, in which there are again two peaks. And then an example of two trifocal lenses in which there are three peaks. There's an intermediate distance to. What might an EDOF lens look like? Well, this is what an EDOF lens might look like. In green is shown an MTF, the modulation transfer function, of the Symphony lens, in which there are two peaks, but there isn't as great of a dip between those two peaks. And of course, nothing's free. That larger area between the two peaks comes at the cost of reducing the heights of some of the peaks. So I want to thank Mark Packer for allowing me to use some of these videos that just show some experiences that patients can have. So these are two different sorts of monofocal lenses, the Acrosoft IQ and the Crystal lens, which is a pseudo-accommodative lens. I'm not going to go into that sort of lens, but it's in essence a monofocal lens. this is a comparison, again, of a monofocal lens on the right with a multifocal lens on the left. And one of the points that Mark makes is that the multifocal lens on the left, as a result of decreasing that distance peak, actually makes everything look darker. Now, to what extent does this decreased brightness play a role with the patient? I can't comment on that. I don't know. But it also appears to be lower contrast. Okay, and shown here too. Now, we discussed the idea that changing the object, changing the number of lines per millimeter, line pairs per millimeter, will change the appearance of the modulation transfer function curve. You remember that 3D carnival slide image that I showed you, that we sectioned off at a certain number of lines per millimeter and then sectioned off at a different number of lines per millimeter and observed the change in the peaks. Here, we are changing not the object and the number of lines per millimeter. They're the same for all of the graphs that I'm going to show you, but we're changing the pupil size. And that also plays a tremendous role in the performance of the lens. Not just performance in terms of the lens is good or bad, but performance of whether the EDOF lens acts as an EDOF or acts as a bifocal. So here with a 2 millimeter pupil, the only difference between the left column and the right column is that the researchers here built two different sample eyes with different sorts of corneas. So just go with these as A and B being two examples of the same thing, C and D being two examples of the same thing. That the Symphony EDOF lens with a 2 millimeter pupil, as is shown in the top two images, looks EDOF-y. Everything is sort of spread out. There is not this tremendous dip as we defocus. The contrast, the modulation, remains high over a range of focus. However, as the pupil gets larger, this is 2.5 millimeters shown for the bottom two images, and excuse me, it's 3 millimeters that was shown in the bottom two images, and 4 millimeters at the bottom two here. That the Symphony lens looks a lot less like an EDOF and a lot more like a bifocal lens. So not only is the quality of the image overall changed as the pupil size changes, but the lens itself functions differently depending upon different pupil sizes. Again, nice and EDOF-like in the top images, very much bifocal in the bottom images. What exactly is an EDOF lens? We keep on talking about an extended depth of focus, and we saw in terms of the point spread function that it's sort of drawn out, that there's this zone of different levels of defocus over which the contrast remains relatively high. But what is the actual definition? So the definition is an EDOF lens with at a logmar of 0.2, which is about 20/30 vision, should have a range of defocus of at least 1 diopter, over which the acuity remains at least 20/30. So I told you that acuity and contrast are not exactly the same thing. That's illustrated in this slide here, in which acuity remains pretty good for the columns on the right, but you can see that the contrast dips down. So the acuity might not drop off very much in some of those columns on the right early on, but the MTF, the modulation transfer function, the curve of contrast starts dropping off. Whereas on the left, you see that the contrast remains very high, but the acuity starts dropping off. So the leftmost column might be an example of a monofocal lens, the middle two of different EDOF lenses, and the right one of a bifocal multifocal lens. Different point spread functions. Let's talk about some lenses that have been launched even more recently than the Symphony EDOF lens, which for a while in the US was the only available EDOF lens, but now we've gotten into the sort of pumpkin spice latte number of choices with IOLs even within the EDOF category. So once more, point spread functions is viewed from the side. The Acrosoft IQ monofocal lens shown at the top. The Symphony diffractive EDOF lens with the point spread function sort of drawn out. And at the bottom, the Acrosoft Vivity lens. Okay, what on earth is that? So there are two new lenses that we should discuss, new at the time of this recording. One of them is the Vivity, and the other one is the iHance. So let's talk about the iHance first. So the iHance are Technis Johnson & Johnson lenses. This, once more, is the curve that we saw of the modulation transfer function curve for the Symphony. I just want you to get a sense again of sort of we've got that distance peak, we've got an intermediate peak, and not a giant dip between the two. That's what we expect from an EDOF lens. This is what the iHance lens looks like. So the modulation transfer function, the upper left-hand graph there, is shown in comparison to a ZCBU, which is a monofocal lens. So the monofocal lens has this big peak at plano at 0, and then a rapid loss of contrast as we defocus it. The iHance has a slower loss of contrast as we defocus it. But there isn't exactly that second big peak, and contrast is clearly nowhere near where it was for distance. And on the bottom, our old friend, the modulation transfer function as a function of line pairs per millimeter. But it's the top graph that's going to be the most informative for us. So what is this lens going to look like in terms of acuity and defocus? Well, it's going to look like this. On the left-hand side is the acuity versus defocus of the iHance lens. And we see that there is, once more, in the logmar 0.2, there is a little bit of an increase in the area, in the tolerated defocus while maintaining an adequate level of vision. But the range over which the defocus doesn't produce a substantial drop in acuity is only 0.4 diopters. And you'll remember our definition of an EDOF lens, a real multifocal EDOF lens, is that it has to maintain the acuity at a reasonable level over 1 diopter of defocus. So the equivalent curve is shown for the Symphony on the right. We don't get as much of a spread out, spreading out of good acuity with defocus with the iHance on the left. So the iHance lens can be thought of as a monofocal lens that has a little flavoring of extended depth of focus. And it was at not much penalty. So I'm going back to the previous slide, and we see that the peak compared to the monofocal, to a purely monofocal lens like the ZC-BU, the decrease in contrast at distance isn't that great. So there's a little bit of a hit at distance, and we get just a little bit of a benefit in intermediate vision, but not enough for us to really call this a multifocal lens. Vivity sounds like a similar lens. So this is the defocus curve for the Alcon lens, and this lens is compared also to their comparable monofocal lens, and we see that there is a substantial decrease in the modulation transfer, in modulation and contrast at distance. But what we get for that is this very large EDOF area, this very large range of defocus over which good acuity is, a good contrast is maintained. So again, comparing this to the EDOF curves that we saw with Symphony, we can see this big EDOF area with this new Alcon lens. But remember, with the Symphony lens, as the pupil size changed, the function of the lens changed too, from an EDOF to a bifocal lens. Well, the same thing is true with the Vivity lens. As the pupil size changes, the function of the lens changes too. So as the pupil size gets smaller, the lens becomes more of a monofocal lens, as is shown in the green curve. And we get that EDOF curve that I showed you in the previous slide with a particular pupil size, in this case 3 millimeters. I know that there are a lot of variables here, and we want to take into account the size of the patient's pupil, as we see at the slit lamp, to get a sense of what these lenses, how a particular lens is going to perform for a particular patient, not just perform in the sense of being good or bad, but whether the EDOF lens is going to act as an EDOF or whether it's going to act as a bifocal, and what the patient's goals are. Why does this matter? What are the stakes here? Well, this is a slide from 2018 showing that premium lenses make up a substantial portion of the market. And in 2018, EDOFs only made up 3.6%. And that was when in the US there was only one available EDOF lens. Now we've got at least three. The Symphony, the iHance, and the Vivity, although it's not fair to put them all in the same bucket because they perform differently and have got different strengths and different compromises. I just want to leave you with one final thought, which is that all of this is predicated on our absolutely nailing the IOL calculation. When we talk about extended depth of focus and bifocal and trifocal lenses, these are lenses that are going to give us 3 peaks. But in order to get the peaks where we want them, where it's going to be most functional for the patient, we have to have really super accurate lens calculations. And even with modern biometry and modern IOL formulas, our ability to minimize refractive surprise is impressively poor. And as we see improvements in technology for lenses and increase in expectations that the patients have, we are going to need to see improvements in our ability to do the appropriate IOL calculations. This is not my only optics lecture. I have many, many optics lectures, and almost all of them, 30-some lectures on optics and topography and all of this wonderful stuff, are available at no charge to you or anyone else at jyoungmd.com. And if you have a smartphone and want to open up the camera app and point it at this QR code, it'll take you right to my YouTube channel. You can reach me anytime at jyoungmd@gmail.com. And I want to thank you for weighing through this really complicated but really important topic and being able to, when a rep from a company tells you all the virtues of a new IOL, to say, show me the MTF, show me the defocus curves, so that I can understand how I can optimally use this lens.